hardly ever is the exams or the homework like, man, did you really get that syntax just right? Did you like study really hard all the esoteric material and make sure it's LR the right thing? Is like, more it's like, can you link all this stuff together and take the big concepts and mush them together to come up with a result? That's what we're trying to go for. So you'll find that grading should be pretty lenient. You can always push back on the homeworks. We have graders doing the homeworks. But me and Matt and usually some of the GSIs and IAs will do all the exams. So you can always push back if you find some like little litigious error that they're after you for lots of points, push it back. What other questions do you have? Maybe one last homework question? Not the homework questions I was expecting. Okay, let's get started. All right, so today we're going to talk about interrupts. But first, let's do announcements. So homework's due today. Have office hours on Thursday. There'll be no new homework assignment this week, so you can start studying for the exam. Practice exams are on the website. We'll have an in-class review on Wednesday. Guys can ask lots of questions. For your exams, we used to do exams like this where we'd give you lots of information and then it was a big test. Can you synthesize all this information as fast as possible in the time and then apply it? And I thought to myself, I've been an engineer for a while and never ever have I been in a situation where my boss was like, okay, the company's going down and if you don't synthesize this data sheet in the next 35 minutes, everything is gone. I thought, well, why are we testing for this? Maybe if you're like a test pilot and you need to synthesize your shuttlecraft is exploding processes and you have to synthesize information quickly, great. I don't think any of you are trained for that. So what we're gonna do is we're gonna release the data sheets beforehand, probably Wednesday night, and you guys can review them and read them. And they'll be like the data sheets you have now. And you are expected to understand the material in there. And then when you get to your exam, you can focus on, well, how do I use this information for my exam rather than how fast can I read it and understand it? Yes?
Can we talk about the data sheets together?
Yep, you can talk about the data sheets, and I encourage you to post questions on Piazza. It turns out that me and Matt write the data sheets, and we're humans, and sometimes we do things that are confusing. And so you could just write to us in Piazza and say, hey, this address looks bad, or I don't understand the phrasing of this, and then we can update the data sheets. We'll let you all know. Yeah?
About how long is the exam data sheet?
I don't know. Let's see. So here's the website. You have one of those. There's the exams. There's 2 exams in the past. You'll get a reference sheet with your exam. You can't bring notes in, but it'll have more or less this information. It might have slight modifications to it. We'll provide this to you because knowing all those instructions is probably not that useful for you. Here's an example of an exam data sheet. So a lot of it is just the formatting which you would expect to see in a real data sheet. In 473, they'll give you a data sheet and be like, all right, you got 30 minutes to understand that, get to it. I'm gonna try and make it a little bit simpler for you because you're not in 473, but this is what you would see. Here's a data sheet for, what is this, motor controller, and here's some inputs and outputs. Great, pin assignments, just like you'd see in a normal data sheet. And what else is in this? Some more pin assignments, a basic description of how to use it. So 2 pages for that component. Now, a normal thing is about 35 pages. And I could give that to you, and it would be fun, but you probably don't know yet what to focus on, right? Because a lot of students come to me and say, how do I read a data sheet? Right, you have to figure out, the whole goal is figure out what the chip does and then find your information. And so we're trying to reduce the amount of information so you focus on what you need to focus on rather than wading through 35 pages of data sheets. This particular one, we have our mythical MAT32 controller. Just like the microcontrollers you're using, only we've specified a certain thing. Here's a pin out. That's the number of pins on the chip. Things got registers, GPL registers that do things. There's a description. It has an internal temperature sensor. This looks like just like your data sheets you've been looking at, only super simplified. Yeah, and then this was just the reference sheet attached to the bottom of that. Does that make sense? What questions do you guys have?
Yeah. Will there be practice exam?
Good question. Right here, practice exams. There's blank versions, there are solutions, and there's data sheets. Yeah.
So are we getting a copy of all of this before the exam?
Yes, you are going to get this on Wednesday. You can review it, and then during the exam, I will hand this to you. I'll hand you your own copy of the data sheet and the reference sheet.
And we're not allowed to bring anything into the exam except for a pencil.
Pencil, you can bring a basic calculator if you would like. Yep. Maybe a straight edge. Probably not. I mean, sometimes they're just useful, helpful to have, you know, like, I get nervous, forget how to add, you know. Sometimes it's nice. Usually, some years I've had hex conversions where it's important to be able to do that. You could have a fancy calculator that helps you with that. I'll try and put hex tables on so that you can actually just look it up. You don't have to remember how to convert hex in your head. I don't know if that's a great skill for 373 students. You guys should be able to use the internet for that. What other questions do you have? Yep.
So because I know there's like a lot of us, so it says like we have everyone's in, oh, never mind, right over.
Well, yes, we are going to be down the hall in a big lecture hall. It's about 3 times the size of this room. There'll be plenty of seating for everyone. Students who have alternative test combinations, please contact me. I'll tell you where you're going to go. Have other rooms reserved. What other questions do we have? Okay, great. What else do you need to know? Yeah. Yeah, I mean, just as part of, I don't think any of this is fundamentally different than what you should have seen in your data sheet. It's just condensed down to like the essentials of what you need to know. Basically, if I was studying for this test, I'd try to understand what all this information is and generally think to yourself, how would I use this? And a person who kind of sees how the exams are put together could probably take the data sheet and be like, all right, I know what part 1 of the design problem is. All right, I could even try it myself beforehand. Right? You can probably figure out what most of the exam is. You might not have all the details correct. Okay? All right. Oh, what are we talking about? Yep. There is lab this week. I had a student that thought there was no lab. Go to lab. Enjoy lab. It's a longer lab. It'll be fine. We could just make it due this week as well, but then we thought with the exam, there's a lot going on. We'll make it a little easier for you, and there's a little room in the schedule. So that's why you have a little bit extra time, or 2 weeks for this lab. There's a schedule. I was going to talk about labs. Great. Yeah, it says finish lab 3, start 4. All right. All right, so now we're going to be talking about interrupts. There'll be 2 lectures on interrupts, so polling versus, we'll talk about different types of interrupts, when to use interrupts, and it'll lead into the interrupt vector controller. So really, interrupts are the way in which we are going to deal with asynchronous events on the microcontrollers. So having a little piece of computational element that you stick somewhere and just computes pi or some function all the time is kind of useless unless it's interacting with the world around us. So that's really the thing that microcontrollers can do that general purpose computers don't do. And so to do that, that means we're going to have to deal with these asynchronous events. So how do you know, what are some ways in which we can figure out what's happening in the world around us? Yeah. Sensors, and how do you know, that's a good point, sensors are buttons or something, but how do you know if an event is occurring on those sensors? True, those could also be something that is sensed, but how does your core know that anything's happening on the sensor?
Interrupts.
It's true, what's an interrupt?
It's a call to a function, but it's not simply
Okay, fine. You're very smart because you're actually paying attention, that's very good.
Reduce through current or voltage.
Yeah, but your core doesn't know that. What's another way? What's the most obvious bleeding obvious way that you've done it so far in lab.
We send a read command
Right,
to the peripheral
right,
and see if anything comes back.
right. That's exactly, so that's the method you have now of understanding about the world around you, right? You have to tell the microcontroller, the core, to go do something, right? And that's fundamentally limited, because if right, if you only say, okay, did event occur, and you have to go ask every single time, you may miss that event, or you're not able to do something else. So we're getting to the point of, mostly we're talking about polling, which would be to go see if something's on the pin, and interrupt is a pin takes action. You set up some event, you configure a pin to take action when a certain event happens. So instead of asking, is that GPIO pin a 1, is it a 1, is it a 1, when it turns to a 1, then something occurs which changes your execution of your program. So I consider polling kind of like texting with your notifications turned off. I have to basically look at it all the time. Right? What you want is something that will notify you that an event has occurred. Another downside of polling isn't just that you have to keep looking. You could say, I could go looking all the time, or every once in a while, and humans are pretty slow, but it really limits your ability to get things done. So in this case, it's pretty easy. You're going to load from a register, and you're going to store. So you're trying to make a LED go on when somebody pushes something. One cycle, you can go and load in from that pin, see if it's been pushed, and then go store a value into the LED. So this is actually not that fast, not that bad, right? It takes 3 cycles effectively to respond to an event, so you're very fast, you're very responsive, but you just can't do anything else useful. That's the problem with polling, right? If your task is to do 10 other things and you want to be responsive, well, that's all you get to do. So you waste a lot of CPU power on this one. You can kind of look, as we think about this as moving to the limit. Here we're going to go and do some work for a while, 100 cycles. Now we've taken our latency down to 103 cycles. And maybe that's okay for humans. Humans are pretty slow, but if you're trying to respond to some digital waveform coming in and react appropriately, or store, imagine you have a serial stream of 1s and 0s coming in on a pin, and your job is to capture those and put them into memory. You might not want to wait 103 cycles. And so now we're down at 70, or only very low, or utilization increased, but where latency decreased. And you can imagine as we increase the amount of things we do, that latency is going to get worse and worse, especially if you're trying to look at multiple things. So this is all just to motivate you to think about polling things is just not going to be a real effective method for almost any way of understanding inputs from the external world. It just doesn't work. All right, any questions? I know I beat that to death. Yes? It takes too much time. It doesn't allow you to, well, you see the trade-off between utilization and latency. So if I have a big program running, and you may miss events. Now, human events are pretty slow, so those are okay, but say you have some transient, I don't know what it would be, motion sensor, and you're off doing some function, you might miss the edges of those that rise and fall, or you might miss the rise of that motion sensor because you're off doing something else and you didn't pull at exactly the right time. And so I guess you have to think about what's the scale of your application, but there are lots of things that happen very quickly that you need to go and measure this event, and you can't just pull. It's just not an effective method. Okay, so we can do better. So interrupts. This is, Merriam-Webster says, this is a break from normal execution flow. So there's different types of interrupts. So we have interrupt service routines, like I've kind of been describing. This is something purposefully interrupts from the external world, like you configure something at GPIO pin, maybe a timer goes off, something you have purposefully configured. You can think of these as just glorified procedural calls. It's just that somebody else called them, right? You didn't actually call them. There's another class of interrupts. We call them instruction, or we call them faults, exceptions. These are typically things that come from the hardware itself. So say you've tried to write to a memory edge, or say you have a bus fault or something. That's not you didn't intend that to happen. You're not trying to take action yourself as a programmer, and it's usually the system failed in some way. So that still is going to throw out an exception. It's just not part of your main program. So we usually call those exceptions or system faults. Sometimes you call them traps. And it's just clear to understand that there are some things, interrupts that will occur because of the core of itself, the things that ARM has programmed in there to keep the processor going, and then there's things that will help you get your task done, setting external interrupts for GPIO pins or something. Yeah. Oh, and I would say that you can also, there is an edge condition, not edge condition, but it can be sometimes useful that there's actually instructions that you could write an instruction that will cause an interrupt to occur. It's nice for software debugging, or say you want to enter a interrupt subroutine on software. I mean, I'm sure I've done it, I don't remember the case, but there is a way to do that as well. Okay. Yes. When I mean external interrupts, it's typically how we think of external interrupts. We mean external to the core. So a timer going off. Remember from the first day of class, I showed you the big scary tree and everybody's eyes glazed over and some people left the class. There's timers on there, and those would be considered external interrupts, even though they're still on the die, just because they're external to the core. And we'll talk about configuring them to do work for you. All right. All right, so quick overview. What didn't I say? Yeah, hardware. Okay, so hardware, sometimes firmware generates interrupts. You need to determine which interrupt is being fired and what code is going to be executed. You're going to halt the program, and you're going to enter this special function called the interrupt service routine. When that's done, we're going to return to the processor. And it's going to be, the great part is this is completely transparent to your program. Your main program that's running has no idea that that interrupt went off. Yes, there's probably some clever ways that you could inform it if you needed to, but generally speaking, code execution occurs independent of interrupts. It's just there's a delay in that execution. All right, so why don't you take 90 seconds to brainstorm, how are you going to get an interrupt, say your timer went off or your GPIO went off, how are you going to get the core to understand that there's an interrupt? What's the nuts and bolts physical mechanism that we're going to do to inform the core that there's an interrupt? Go ahead and brainstorm. All right, so what are some ways that we can get these interrupt signals so we can inform the core that is something's going on?
Maybe we add a bit to our bus that's just like, it's like active when there's an error or an interrupt.
Sounds good. Tell me more. What do you mean when you add a bit to your bus? You mean like a special packet? What are you thinking?
Or, yeah, just like add a signal.
Okay.
A 1-bit signal to the bus.
Okay, so when we talk about our APB bus, we could add another line. We had like P ready and write. We could put another one that says interrupt. Okay. You're getting there. I like that.
There's some sort of interrupt controller in the core.
Yep.
You could write to that
How? What's the mechanism?
using
Okay, how does a peripheral tell the bus controller or the initiator, I want to speak right now, take my packets? I thought it was the initiator that was selecting which one would be controlled.
Send the signal directly from the peripheral to the intercontroller, bypassing everything.
Bam. Nailed it. You'll get your check in the mail. Thank you for pushing the lecture along. Basically, that's exactly it. There's up to core specify, or ARM specifies up to 240 interrupts are possible. That's the most lines that could be added, although your particular device has fewer. And so basically, your GPIO, all these things will have interrupts, and it is a bunch of wires that are directly put into your interrupt vector controller. We'll learn more about that in detail, but that is the idea. You need an extra path. The problem, now I'm not blaming the folks that thought about going through the bus, because that's the only mechanism you thought of, we had so far, but the problem with the bus is the controller isn't going to ask all the cores. They're not going to go and pull the cores, or sorry, the peripherals and say, do you have interrupt, do you have an interrupt, do you have an interrupt? And plus, you don't want to go through all that latency. You want this thing to happen directly. Did you have a question? All right. Yeah, so they call them IRQs, interrupt service requests. They're basically a wire that goes over. They're going to be mapped, so you're going to have N wires. They're going to be mapped to hardware, which we'll see in a bit, that will go and make it in the NVIC, so it's the Nested Vector Interrupt Controller. And those will decide what happens when these lines go up and down. Okay? So let's just look at generally what happens. So we're going to obfuscate the actual effect of how this line turns into code running. We'll actually talk about that in more in the next lecture. But we'll just say, let's assume that fact is true for right now. So what will happen is that your program will be running along, fantastic, it's doing its thing. Some external event will occur. You need to go and find, we'll talk about this mechanism, we need to go figure out, or at least the core needs to figure out which of the wires that come in, which one corresponds to, say, a particular interrupt. And this is an example of vector table we'll go into in a minute. Basically, it's a bunch of memory locations with addresses in them that point towards the actual interrupt that you're going to run. So you go and say, aha, this is the interrupt I wanted 5C. Then I go over to the interrupt, I execute the interrupt. When I'm done, I go right back to main, and then we're done. Okay? So from a conceptual level, does anybody have any questions? Yep.
I guess, like C++, you have like an exit command that kills main off. If our interrupt service is stopping our program, how does that work?
All right. So say you halted or there was a fault or something.
Yeah.
Well, these little microcontrollers don't have all that extra functionality built into them. So one way in general, which is not specific to interrupts, is that you deal with that is there's on the peripherals there's something called a watchdog timer. And so what you do is you would set it to count up to a certain value. If you ever get to that value, hard reset the entire microcontroller. And then what your job as a programmer to do is to go through every so often within that time frame and just reset the counter back to 0. So that's proof of life. The fact that the core can go and do that function of actually resetting the thing means that you're in a good state. And if that can't happen, you're in a fault somehow, then the thing will automatically get reset. Not probably the answer you're looking for, but that's probably the best mechanism we have. Yeah?
It's like our interrupt service can have an infinite while loop in it.
Yep.
And just wait for the watchdog to go on.
Yeah. That would be horrible. Don't do that. And the watchdog is something you have to purposely set up.
Oh, okay.
It's not always inherently on. Yeah.
Is an interrupt vector table a stack? Because I saw it says on top of stack, so is this just a stack? So
Where we're going to see in a few slides that this is actually located at the very beginning of memory. This is memory address 000. The top of the stack is a value in there, and it's telling the core when it boots up, this is where the stack is. And then the next thing is the reset handler, which means when you power up, you don't just get to go in main. That's not how life works. There's a bunch of other stuff that happens behind the scenes. Stuff like The hardware itself has to go boot up the buses and make sure all the clock distribution trees are configured correctly. There's all these other things that have to get up. In the processor has to be a good, stable state, and so your reset handler will do all that for you. Reset handler is just a program that's been specially optimized, usually from STM, to boot the thing up into a known good state, and then go forward. All right. So you guys are jumping ahead a little bit, which is great. So vector tables, let's talk about them. So we think about our memory hierarchy here. Just specifically in the code space, there is flash memory. So depending on how you guys have your labs configured, typically if you're just going to run your code, it's actually going to come here in SRAM space. But the problem is that if you unplug your dev kits, your program's lost. And that's not how we typically use microcontrollers, right? Everything's put into flash, stored there, and then on boot up, you don't want to run your program out of flash, that would be too slow. So on boot up, it copies everything over, all the information into SRAM, and you're executing off that. So sometimes you'll see in lab that you're actually, your base addresses are all up here, where in class, all the examples are down, start here. It's just a difference of, actually no, it's the other way around. But it's just a difference of what your perspective is. If you're running off of flash, then it's going to get copied over. If you're running just on your debugger, then it's always going to be down here, I think. Okay, anyways. In this space, there's the vector table, there's your normal code, and then there's your initial main stack pointer. So we can look in a little bit more detail. So this interrupt vector controller and main stack pointer is here. This is directly from, I think it's a manual. And basically, this is your vector table. This shows you all the interrupts that are available, and it keeps on going, but this will be all the interrupts that are available on your microcontroller. There's system exceptions, which are defined by ARM. Yeah?
I was just confused when, so after it gets booted up from flash,
Yep.
it copies it over to SRAM.
Yeah.
And runs off of that.
Yeah.
I don't know if this is just because of like the slides, but does it stay in that specific memory address? Because it looks like it's still in the flash.
Is that what the memory addresses come out to be if we look at the table?
Well, I don't know if like the slides. It looks like it stays. Oh, I see.
I think this is true, that this would be where your flash is, but it might have been for a slightly different model microcontroller. I don't know. But this is the theory. Just a side note, if you're trying to boot your microcontroller and you want it to run independently, so you power cycle it and it always works, data is going to be stored in flash, or your program is going to be stored in flash, then it's going to be transferred over to SRAM so it can run faster. I understand that's confusing. I will update these slides. All right. The more important thing for when it comes to interrupts is the interrupt vector table. So, so the vector table is simply a list of functional addresses, function addresses that are stored at the beginning of the memory. So the exception here is the top is 000, which is your main stack pointer, or at least shows you where the top of the stack is. These functions are called interrupt service routines. So for example, if you're calling this one, right, you're going to go run into your interrupt service routine handler. It's going to boot up the device. You have system talk handler, external interrupt handlers. They're just memory addresses that are, it is a memory address, but there's an address stored in here that tells the program, here's what you're supposed to go and do. In fact, the program pointer is initialized not to 000, but it's initialized to 04, and will jump to that location right off the bat. So if this gets into your program counter, then you're going to be running the interrupt service routine, which is the first thing that needs to happen when you boot your device. Yeah, stack pointer, that means stack pointer. Initialize PC. Yes, what questions do we have so far? Okay. So you're going to need to go and look up an IRQ. Oh, I should have said this before. These system exceptions are defined by ARM. They are non-negotiable in the sense that this is what the core needs to function. The ones starting at 0 or hex 40 and above are implemented by your manufacturer, so STM, Cypress, whoever makes that microcontroller. That's where they're adding their special intellectual property, and they have interrupts that will deal with that intellectual property. ARM is trying to make your life slightly more difficult by saying that these have negative exception numbers, even though there's no such thing as negative memory space. They're saying that this is a negative exception number just to give you the connotation that this is one of ARM's special things. This is reserved by ARM. So when you see, oh, I have a negative priority or a negative exception number, it really means one of these, 14 from ARM. Okay. Yeah. And so say you get a IRQ, let's see. So this is interrupt service request. This is going to be handled by the NVIC, which we'll go over in more detail next time. But the NVIC's job is to go figure out where the IRQs are, or sorry, what IRQ is coming in, and translate that into what the program counter should do next. Okay. Yes, system exceptions, I said that. Fantastic. Okay. The program status register, which we've talked a little bit about before, this is the thing that has your, your ALU flags, your overflow, your carry, your zero flag. They also, in this register, tells you, well, if you're in an IT block, which is not really important for this class, but also tells your exception number. So you have 0 through 8 bits telling you what exception you're in right then. It's rare that you would have to be in your program saying, okay, what exception am I in? The hardware is going to take care of that and boot you into the right interrupt service routine, but this is where it's kept track, okay, of what's being executed at that moment. The program status register is also divided by into these 3 registers that are individually addressable, but really they're all just the same address or same register. Okay. So say we're going to get the IRQ line 7 goes off, okay, and you need to figure out what address that is. Well, that was the external address for external interrupt. So that's up there at 7. That's external TI1 IRQ handler, and you got to go and figure out if that's the 7th one here. How do you go over there? So basically, the mapping's pretty straightforward. Just there's a basic equation, right? The 7th times 4, because we're going indexing by 4, and then plus 64 for the offset in those addresses. And that will give you X5C, and you see that is the memory address. So essentially, this is what your NVIC is doing. Your NVIC is saying, I've got the 7th IRQ going off for 7th priority IRQ. I need to do the mapping to tell the controller what code to execute. And now, in that case, it's 5C. This is all to make up for the fact that ARM wanted to give you these negative priority numbers, okay? And that would be the case for the system talk, which is essentially a negative number. All right. Let's see. Okay, so let's go through basic example here. You have a GPIO, you've gone and configured it so that an external interrupt, so say a pin with a rising edge. So what's a nice thing to think about is that your pins can be falling edge triggered, rising edge triggered. So if you're looking for a particular part of the waveform, or maybe a sensor goes low and that triggers some event, you can set up an interrupt to look for that rather than trying to say, is it just state high or low? You can look for the edge. And that's going to cause some event to occur. Then the IRQ line goes to the NVIC. And the IRQ, so in this case is IRQ number 9. The NVIC is going to go and look at this. It has to go look into the vector table, do the math to figure out what is the next instruction that must be run. So that's, again, a small amount of math, but it still needs to be done. Then it resets the program counter to go after the value that's held in that memory address. Okay. And then you're going to go off, change the value and start executing the IRQ handler. Okay, so question for you. Oh no, I gave it away. Oh no. Well, I'll just tell you. So their interrupts are just fancy function calls. Some pin goes high and some code gets done. We know that the ISR must be ABI compliant. It wouldn't make sense otherwise. It's not like you just can just run some arbitrary code and mess some registers up. So take a minute to think, what are the registers that need to be saved? Yeah? What, okay. What other registers would you need to save?
0, 1, 2.
3? Yep. So the bottom 4, got to save those. Those are just required anyways, just to be ABI compliant. But you'd need to know where the program counter is. What other information would you need to know?
You need to know registers 4 through 8 and 10 through 13, I think. You need to save those values before the execution. So like push them to the stack.
That would be true if we were, yes, it's a good idea you got to save the state of your device, yes. But if we're going to be ABI compliant, we can assume this function is ABI compliant, and then we'll tell the interrupt service routines that we're going to write not to go and use registers R4 and up,
Okay.
right? So we can at least say from that point of view that the state is going to be preserved, or it's our responsibility to make the state preserved. What are some values, we talked about program counter, that inherently won't be preserved?
I guess for the next line of execution, once the interrupt is done.
That's true. You got to know what that is. Yep. What are some other things? Link register. Anything else? Yeah. Huh? Any timers? I don't think the core needs that. I was thinking stack pointers. The timers will just, so say you go up and set a timer off in some peripheral, this is going to keep going. It's not going to be affected that if you're doing it, that it's not going to be affected by you having an interrupt, but maybe you should think about the interrupts should inherently be short. You don't want to interrupt that's really, really long because that's going to drastically change how your main is executed, so you may miss timer events. However, if you're if you're within, I don't know what the correct number is, but if your interrupt service routine should be short so they don't really affect the rest of your program. I have written entire programs that are basically all interrupt service routines, one right after another one, and there's almost no main. You just go into main, you just do a while one. But still, they should be short. Okay, any questions? Yeah.
What if there are 2 interrupts and they are very close to each other? In that case, the interrupt doesn't have time to execute.
Yes, so that is the job of the NVEC, the Nested Interrupt Vector Controller, and we'll talk about that in our next lecture on this. But yes, those are edge conditions which we're going to have to be concerned about. When there's multiple interrupts going off, which interrupt you service first, which one has the higher priority. If your interrupt goes off, if you're doing, I don't know, some basic timer thing, you're spending a lot of time there, and a more important one goes off like a system fault, you have to be able to choose which one to go off and need some mechanism for that. All right. But before we get to some of those details, let's talk about the mechanisms for transferring control of the processor from the main function to this interrupt. Okay? So let's say we are in our user program, some interrupt signal goes off. What we have to do is what's called stacking. We have to take the state of the register of the core and preserve it so that we can go and do our task. And when we come back, we're going to reinstantiate that state. So what we're going to do is we're going to, we have the old PC, or stack pointers pointing at some value, and then we're going to save the program counter, link register. I guess we're not saving the stack register. My apologies for saying that. My brain is old. R12, which is the interprocedural register, and the R0 through R3. Why do you have to save the program status register? What's in that program status register?
Flags, like.
Flags, yeah. So that's primarily, when I would think about this example, there's many things in that register, but the status flags over ALU. So if you just did a comparison, and your next instruction would have been a branch based on that comparison, and you leave for interrupt and come back and all those flags are messed up, well then your next branch instruction is not going to be executed correctly. So you need to retain that information so that the core can go back right where it was. It would be somewhat inefficient, at least from a memory point of view, to store all the registers. So from the ABI compliant point of view, we're not going to worry about 4 through 11. Okay. All right, so then you go and do your interrupt service routine. You exit your service routine. You unstack, and you're back to your program. Okay? Now, this is all done in hardware. You don't have to go through and actually write a program somehow magically that like anticipates when an interrupt's going to come, and then you push stuff and pop stuff. This is all done for you. When you land in your interrupt handler, you will be in a good state, and everything will be saved for you. So you don't have to actually do that task. There are some nuances. This is not this particular slide, and this nuance is not that important for this class, but your microcontroller does have basically 2 stack pointers in it. You have the main stack pointer and the process stack pointer. You'll see this in the documentation, and it confused some people some years. So generally, what would be reasons why you'd have 2? Can anybody guess? Want to guess?
We have 2 different things. We have the main and we have the interrupts.
Sure, you could do it that way. Anything else?
One's running to the main program and one's keeping track of the subroutine.
Yeah, that's kind of the same idea. Do you have a different idea? Those are good ideas. That would, in the context of what you've learned so far, makes a lot of sense. What they're really doing this for is if you have an OS, like an embedded OS running on these things, which is totally plausible, and you'll have one for your main OS, and then you'll have one for your applications. So that's generally why they've implemented this. Now, there are some nuances depending on what mode of your processor is in, which stack pointer will be used for your interrupts. However, in the context of this course, if you're not using an OS level thing, everything is going to default to the main stack pointer. So there's going to be no difference between, you're almost never going to use a process stack pointer in this course. And so we can just, for the rest of these examples, we're going to assume that that difference is not that important, which mode we're in. But it's just good to know that that is a possibility. So there are different control modes. I think I said this, yeah. So basically for applications with without an OS, you're going to use the main stack pointer all the time. You can actually find it if you want to dig through your tools. Here, this is you're in a service routine, and you're using your main stack pointer for this mode, and it tells you that what handler mode you are and all that sort of stuff. The points where this actually comes somewhat interesting, or at least again more relevant to this class, is how we're going to use the link register. Normally, link register is your way back to your previous instruction, right? So it links back. In interrupt mode, it points to tell the controller whether you're going to be in main stack mode or program stack mode. And the reason that's important is that we're going to replace whatever's in the link register with this value when we're interrupt. And you're going to be like, why are you doing arbitrary horrible things? The arbitrary horrible things is in case somebody wanted to put an arbitrary horrible OS on this, okay? So in this class, you're almost always going to be in threat handler mode for working with non-floating point extensions, and then you're going to be, that means the stack pointer equals main stack pointer, okay? So the last 3 slides were trivial details you don't need to know about, except for the 4 people who really care and will get very, very confused. There we go. Onward and upward. All right, so let's go through an example of how this would work. We have a program, main. We have a systic handler, which is the internal clock that the core uses for timing. So every Cortex M0 M4, whatever it is, M3 comes with a timer, or at least one, and that timer is used internally for timing events, and you get to use it for some of your events as well. Anyways, and we'll talk more about timers later on. We have our registers, and then we have memory looking at our stack pointer, for our stack pointer. Okay? So let's say here, some interrupt occurs. Okay? We're going to, so let's see, we're just saying we're going to assume that we're in main stack, or yeah, the main stack mode for this class. And the interrupt occurs, and now we have to do stacking. So we went through and we stacked all the values, the program status register, PC, link register, R12, R3 through R0. We've changed the link register to this value. This is an indicator of what needs to be done when returning from a function, that the hardware has to do something special. In this case, what's the thing that special thing that has to do when it returns from this function?
Burn a bunch of registers.
Has what?
Fix a bunch of registers. Fix a bunch of registers.
Fix a bunch of registers? What's the term we use for that? No, unstacking. Yes, we have to pop, which is like a mini version of unstacking. Okay, you're all getting there. So that is to tell the processor, hey, this is what you're supposed to be doing. This is like the special instruction, essentially, that says, don't just branch back. You have to do, your branch is a special type of branch back, which is to unstack things. What else is there? Oh, and the program counter has changed, I believe. Okay. Yep. All right, so now we didn't label this with memory addresses, so we'll just have to take my word for it that that memory address points there. It's going to do things. We're going to, let's see, what do? We updated R3, update R4. Then when we link back, we have to, the LR now is FFFFFF9, which tells us to unstack. So we're going to take all that and push it back on the stack. So we've updated all these things. Okay? You can see the error condition here where our program was not ABI compliant. It should have been, and R4 has been changed when it shouldn't have. So now there would be poor execution, or incorrect execution, yes.
Let's say we had other things saved. It goes to the interrupt. It says to unstack. How much does it know to unstack? Like, what if there's things saved before? Does it just unstack the whole thing, or just a certain amount?
It will only unstack. Well, I think what you're saying here is, say I have a bunch of data here, right? I've gone into an interrupt service routine. The interrupt service routine needs none of that data, has no idea what it is. It goes and stacks, does its job, keeps going forward, unstacks, and then returns the processor to the state it was in. So there's no condition where it would need to know things above that stack pointer. Is that, yeah?
I guess my question is, R4 is why is this API compliant right now?
It's not.
Oh, okay.
I think I said that. I think I said, well, maybe I glossed over it. This is the error condition. That should not have happened. I'm just reminding you that this should be API compliant. R4 should not have been manipulated right here. Yeah, I'll make that super clear on the slides. I can see how somebody in review would be confused. You got to speak real loud, I'm old.
What part of the sysdig handler subroutine tells the program to unstack everything in the front?
Link register. So basically it gets here, it says link back to your link register, okay? Fantastic. And your program says, okay, I'll do everything I normally do, which is just take this value and put it into PC. However, this is a special value. And so your hardware knows it's a special value. And when it sees that special value from the link register, it knows to unstack. Well, let's go over there. I haven't seen these hands.
This special like stacking, unstacking
Yep.
routine with that specific link register
Yep.
address, that only occurs for specific like interrupts, or is it any time?
Every interrupt.
Every interrupt.
Yep. There's no interrupt. Every interrupt. Yeah.
So I know you mentioned that the register 4 is not, like, doesn't get saved, so it's not API compliant.
Yep.
So how do we make it API compliant without having to, like using just this whole?
So say you're in your interrupt handler and you need a stack because you just run out of space. Then go push it up to the stack. It's just going to go here. R4 goes here, right? No worries. You keep doing all your program, and then before you branch out of this, you need to pop what's in the stack. That'll put the pointer back up to here, and then you go forward.
And that would make the whole program then API compliant.
Yeah.
Let's say we forgot to pop off R4 in the situation.
Oh no.
Does unstacking go back to the previous stack pointer, or does it go back up to predefined amount?
It should go back up a predefined amount, and this is where we get into the intricacies of the program stack pointer and the main stack pointer. Yeah, painful.
When was the initial link register, like how did it store the initial address? There's no branch instruction before in the main.
An interrupt occurred. So up here, interrupt occurred. How did you know where to go? And this is the part where I didn't tell you all the details. I'm trying to get you to get the general ideas. And so the NVIC, so an interrupt service routine line went high. The NVIC said if line 7 goes high, it figured out what address you needed to branch to, and then that's where the address came from. Basically, a piece of hardware is saying, okay, you need to go here now. It changes the program counter and then initiates stacking. I know there are more hands.
So like store the register once it's done with the interrupt and like continue maintenance, store the link register as well. Like how to pick up the address?
So link register is stored up there.
Yeah.
Yep. And then it just puts a special link register in there.
Okay.
Yep. There's got to be another question. I saw the most hands I've ever seen. I've been the most confusing I've been so far. Fantastic. Yeah.
Or even the least confusing, we know you know to ask you questions about it.
Okay. Ask me more questions. Let's see. Yeah.
For the exam, are we expected to understand the base level of interrupts, or will like next lecture's information also include on?
Interrupts will not be on this exam. Everybody's blood pressure went down. Everybody feeling real good. Okay. You still have to pay attention, though. That's why I didn't tell you at the beginning of the lecture. You have to pay attention. All right, what other questions?
Sorry, last question. So for the link register, I still don't quite get it. For FFFF9, I don't see any address on this picture having the address have the value of FFF9.
FFF9 is not a physical address that you link to. FFF9 is a special flagged memory address that the hardware looks at, and when it says, if you're trying to go there, we're not doing that. We're going to unstack instead.
Oh, this is just instructions, just like it.
It's a piece of hardware, a combinational state machine that's looking for, whenever you're doing links and trying to put your link register into your PC, it's going to check it to see if it's FFFF9. If it's FFF9, then we're going to do something special. You can't have negative numbers here. It's not like it's a Tukes complement. It's not going to be confused with anything, right? And I guess that memory address would technically be up in the system, the reserved system area, and the system has reserved that for the special task of telling the controller, the hardware, to unstack. Okay. So we go through there, we unstack, we did a thing. Going too fast today. All right, we'll go to the next slides. I don't care. Great. I'll pull up my next slides. So basically, the big deal was we're talking about polling versus interrupt. We're trying to convince you that polling is bad. The peripherals have this extra data bus associated with them, which is a line that goes off and raises an interrupt when that occurs, or raises tells the core. The NVIC is going to go through and figure out, this line went high, what do I have to do? What is the thing I set my program counter to? It has to go look up in the vector table. And then you look at the vector tables in the beginning of memory, it looks it up, and then you have to do stacking and unstacking to preserve the state of the core. All right? All right, so next we'll talk about vector controllers. We'll take 30 seconds for me to get my slides up. Yes?
For the external interrupts, do they all need like a synchronizer? Because the signal is not synchronized with the clock on the.
Yeah, I mean, when you say synchronizer, you mean like a metastability? Yeah. Yeah, at least those are all on device, so life gets a little bit better. But yes, those things can come in completely asynchronous, and they are going to be processed on the next clock cycle.
So whenever you have any kind of external signal, you always need the.
Pretty much, yes. If you have asynchronous signals that are going through between different clock domains, you need some way to ensure, it doesn't have to be a synchronizer, there could be other methods to ensure that you're not trying to sample data on the edge of the transition. Nope. Haha. They will be later. You guys can do it the old-fashioned way. Other questions? Okay. So last time, open questions from last lecture is how do you actually set up and control the interrupts? Some are more important than others, and what do we do? This guy brought up the question of, well, if you have multiple going off at the same time, how do you choose which one to do? What happens if you're processing one interrupt while you're handling another one, or another one comes in while you're handling? And what happens if you're in a critical section of code which you really can't be interrupted, right? I don't know. You're on the James Webb satellite and you're configuring something, and if this thing gets messed up, you're pointing your receiver dish off axis, and now you're never going to receive another instruction again. There are certain times when you cannot be interrupted. So how do you handle all those things? And the general responsibility for this is called, is the nested vector controller. So this is a series of combinational logic and state machines. You don't program it, you configure it, and it does a bunch of tasks for you. All right, so interrupt control registers, we talked about this a bit, that there's these exceptions. So there's registers that have the system exceptions, and thankful ARM's denoted those to be negative, essentially 16 through -1. And then you have your normal interrupts that your manufacturer has created. Okay. Yep. Your particular device doesn't have 240 of its own peripheral interrupts. It only has 96. Why do you think that they would, why not have all the interrupts?
Noise, expensive, adding extra crap.
Expensive, I'll go with that.
For educational purposes.
For educational purposes. That's L2CK. That's a.
That's what I'm going to say just now.
What's that?
That's what I'm just going to say.
Okay.
Maybe the other ones are being used for the board?
No. These are all the ones that have been implemented. Interrupt nested vector controllers are just complicated pieces of hardware that have lots of little edge conditions, and so the more complex it is, the more space it takes. So I think you said cost, the more energy it consumes. It's just the complexity goes up to the point where the flexibility of being able to have GPIO pins, and you can configure them to like negative edge or positive edge and all these things, all the extra complications isn't worth the effort, basically, the extra functionality you get out of it. Yeah.
Would we be able to use them like if we tried, or are they just reserved, like not even configured from?
They don't exist. So if you try to go place something in the table, your NVIC will never know to go there because there's no line that goes high that will ever be called in that table.
What type of engineer programs the other 240 interrupts?
What type of engineer does what?
Programs the other 240.
I mean, that would be an architect. So you're getting the ARM core from ARM. You say you're working at STM, and you've got this intellectual property, which is a bunch of RTL code, so basically Verilog code. And you're saying, your manager says, okay, we need a device that has this many peripherals and this sort of thing, and now your job is to figure out how to glue everything together. And so you would write RTL, so Verilog, essentially to go and say, okay, from my peripheral, I want so many interrupt lines to go to my INVEC. And I don't know the process exactly of like what probably ARM gives you a big INVEC and then you can like hack off parts of it. I have no idea.
Just to clarify, the Cortex M is like the ARM intellectual property?
Yes.
Okay. STM is the implementation.
Yeah, so ARM essentially gives you the core as a software file that you would buy from them, and then you would take that software and then turn it into hardware gates, and that would be synthesized onto a chip, and then you tape that out. And then typically the vendors are adding their own peripherals onto it. Good question. And so yeah, it's not a trivial job to try and get all these things to work together. There's a lot of coordination, and I don't know how much it costs to get access to the core, but having been on these sorts of teams, typically what happens is somebody at ARM would be your guide, your advisor, be there as your technical representative that will answer all your questions. And sometimes, if a big enough project, they'll actually send people from ARM to work in your building, in your team, to get the job done. Because it's part of, basically it's part of you're buying it and you're renting a person to help you do it. It's that complicated. Okay. Let's see. There are a wide range of interrupt registers. You can configure all sorts of things. You have ones to control the registers, to enable the registers, to clear the interrupts, to figure out which ones are set and pending, which ones are active, what the priority numbers are. For us, we're going to be focused on essentially these, and I would say these are what you need to understand the functionality. So you'll have registers that will set and disable interrupts. So you have that 96, you're going to have registers that say turn these ones on, turn these ones off. Just like we did with the GPIO pins, you would say, I want to configure, GPIO modder configures the GPIO pins. Here you're going to have registers to configure the interrupts. You have registers that can keep track of the state of what things have gone off. So if you have registers that are pending, or you want to set them to be pending, so there's registers for that. What else we got? Here's a register that tells you what interrupts are actually active at the moment, and then you have another one that's telling you what the priorities. So some of the register or interrupts, especially the ones from ARM, the negative numbers, you can't really mess with those. You can't change the priorities. But you could say that I want, this GPIO is the most important thing, and I don't care about my timers, so I want my GPIO timer or interrupts to be higher priority than my timer interrupts. So that means when your core starts executing, it will always execute, if there's two at the same time, it will execute the one with higher priority, which actually means a lower number, which will confuse us all throughout these lectures.
So if the GPIO has a higher priority, then that will cause the interrupt tolerance in the same essence have a higher priority.
Yes. So one problem, and we'll see, is that the way we talk about interrupt priority is confusing, because it's actually the lower number means it's more important. So we're going to try and say the word more important or least important, not higher or lower, because that will just confuse us. But it's my responsibility to remember to do that. All right. So 2 ways to control interrupts. So you can control them directly. There are sets of interrupt registers, control registers, that ARM requires are instantiated. They're fine. totally usable. It's kind of like the bit banging method of controlling the registers. And then your device manufacturers also sets up registers or mirror registers that do the same thing. These are typically a lot easier to use. And as you go through your documentation, you will see that STM is giving you their register versions, even though they essentially do the same thing. So here's just the ARM definitions of how to control these registers. A lot of it is just individual register banging away. Method 2 is, and I mean like here's a function to set individual bits. Here is the same list I showed you before. These are essentially from your manufacturer. It gives you entire register, 32-bit registers or multiple 32-bit registers to control all your interrupts at once. So we'll go over some of those in a second. Here, if you're, is this the enable? Oh yeah, you're going to set enable. Okay. This is the interrupt set register. Here's an example, right? Where basically you're saying, here are all our registers. You have your index number. We're going to start over here. Where we start? Reserve. Okay, fine. Here are the manufacturer controlled ones. You're going to put a bit in these things to set them. So you have a set register, and we could basically, it's a concatenation 31 up to 96 for every one of their registers. So you have the name, the interrupt number, and the index of that register. All right. Again, if you're going to go set registers, here's the maximum you could have for the manufacturer registers. In your particular case, we only have 96 plus the 16 from ARM. All right. So some of the registers are designed funny. They're a little bit painful. If you want to set a register, you have to go and actually put a 1 in there, right? And you have another register that's for clearing. You still have to write a 1 to clear a value. So you have 2 registers, one register specifically for setting the interrupt enable, and then another register address you have to write to, you write a 1 in to clear it. Why would ARM make this decision? Or what? Do you have a question first?
So let's say we want to write a 1 to the last 6.
Yeah.
Then we clear it, use clear. Then what clears the clear?
So you have a register here, and say you want to set it. Say you want to turn on the 0th bit. You want to turn on that thing. You said put a 1. You write a 1 to this register up top. Say you want to clear it. You have to write a 1 to this register. Why? Why would they do this horrible thing? Okay, question first.
So writing a 1 to the lower register writes a 0 to the, or would that write a 0 to the top register?
Yes.
Okay.
Yep. So writing a 1 to the register turns into a 0.
Kind of like emergency situations, like when you write a 1, you know that it's functioning. If something breaks, like a wire or something, it would go to 0, but you don't want that to be like go to 0.
Let's look at normally. Yeah, getting there. So normally you have one register that controls things, and you can write 1s and 0s into it, right? You want the GPIO to be disabled, you write a 0. You write a 1 into that same address, that same location, GPIO goes high. Here they have 2 addresses, one just for setting registers and one for clearing registers, or clearing the same interrupts. Why would they have 2 memory addresses to do the same thing?
Is it to prevent conflicts of trying to set and clear it at the same time?
Well, yes, it's to prevent conflicts, although a single core processor wouldn't do it at the same time. Yeah.
Maybe like a security measure, so that one control everything.
You're getting there. So it's really, this is just a safety measure. It's that you as a programmer don't mess things up, because if you mess up your interrupts, basically the whole thing's going down. Nothing works and it's unrecoverable. So they wanted to give you this extra security method that when you're writing things into there, right, you can't accidentally write into the wrong address and clear into the wrong address. Also, it just does the masking for you, right? So you can just say, I want to put the 1 there. You don't have to read out or it in and then put the 1 where it's supposed to go. Here you just go put a 1 in there. So you want to turn this to 0 or this to 1. You just put a 1 here. Or sorry, I guess you're going to clear this one. You're just going to write a 1 there and it won't affect anything else. Yeah.
What happens if we write those
Nothing. It won't, you have to use the clear register to clear it.
For my earlier question, what I meant was for clear, what clears that? Or you just have to manually set it to some location?
What clears the clear register? Writing a 1 into it clears it to 0. They're just trying to be confusing to you. Once you accept this, life is okay. Does that answer your question? Like, you could write a program that says load or store data into this register.
But then, like, for example, I'm saying, like, let's say we leave it at 1.
Yep.
0th bit. Would it just be constantly clearing that register, or would we have to?
Oh, this is no. This is the state. This is which interrupt should be enabled or disabled. Yep. So it's interrupt set something register 0, interrupt clear something, clear enable register 0. Yep.
So is there like a third register these two are controlling?
Yes.
Okay.
Yes. They're just, I bet there's just a big bunch of AND gates and OR gates in there at 2 different addresses. So you have your peripheral that has probably 1 register in it, and then it has a certain function when you write to, if we think about it like a peripheral, when you write to one address, it has one set of functions. When you write to another address, it enables a different set of functions.
So you can't write zeros to I0.
Correct. So here, if you want to go and set this particular bit, you'd have to shift it over 18 times. You can set it to 1. That will transfer that 1 over to the clear register. Now it's at least represented correctly. If you want to clear, if you want to disable that particular thing, or another one, I mean, so 20, let's say, then you have to write a 1 into there. That will turn it into a 0. Very confusing, and it will update the other side. So it says actively, to change the state of this, you have to put in 1s. Otherwise, it won't change anything. See, I've warned you about this now, so when you're writing your when you're doing this later in lab, you won't be like, why the hell? You can just say, they warned me about it, at least.
So both registers modify the other register.
Correct. There's really 1 register underneath. It's just 2 interfaces into the same register. Yeah. Yes. You guys absorbed the information too quickly. You're too good at your jobs. Yeah.
So you say they're the same register.
I guess I don't actually know, I'm not an architect. I'm going to guess that underneath there's the same state holding device,
Okay.
a bunch of D flip-flops, and then they have 2 different ways of interfacing with them. And so, yes, that's what I'm going to guess happens underneath. Yes, so here, you want to go look at it. This is literally the data sheet here that talks about, the data sheet entries that talk about setting and clearing the interrupts for more clarity. Oh, and there's also pending bits. So these are interrupt bits. There's also a set of registers that tell us, that keep track of which interrupts are pending. So this comes back to the question, what happens if you have multiple interrupts going off at the same time, which is not an unusual case. Things can happen, a lot of things can happen on your microcontroller at once. And so there's a whole set of registers just dedicated to say, these are the ones that are pending versus which is, last we were looking at which ones are enabled. So here's a stack that says, okay, I don't know which one it was, but like, interrupts, 0 and 5 are pending. And those have to be dealt with. Okay? That's where we would keep track of that. Now you could write into that register and say, I want to make, say from a software point of view, I want to write a code that will make this register pending, and when it comes around the next time, it will be serviced. So you can force an interrupt service routine to happen, which is handy. Yeah?
And how do you decide which pending
Ooh.
occur?
Right. So now that's a great question, because now we need some control mechanism to figure that out. And so that's going to be where we define the priorities of each interrupt, where we say that this one is more important or less important than the other ones. So the NVIC will go through, once you set up the registers that say these, you have multiple bits for each interrupt, and then you'll say this is the priority, and then your NVIC will go through and say, okay, look at the pending ones, which is the highest interrupt, or the most important thing, and we'll service that next. All right, there's also an active interrupt status register. So once you've been, and we'll have some diagrams to go through this, but once you've been in pending, and the NVIC figures out who's next, it will update this register to say this is the active one, and this is not writable. You cannot write to this. This is read only. Yeah.
Will there only be one bit active at one time?
Yes. Can you? No, I'm a liar. You can have more than one active if you have, we're going to talk about nested when interrupts interrupt interrupts. I'm waiting all day to say that one. Yeah.
If you want to clear, I think interrupts you would have to go through the ICE.
If I want to clear a pending interrupt, so up here, this thing that was too confusing that I didn't explain well, this is just for enabling or disabling. You're just saying here that I want this, if event should occur that would trigger an interrupt, I'm going to enable our system to respond to it. So you would go in through this thing and say, I got a GPIO pin, when it got on the rising edge, I want you to do the thing. I want you to actually respond to that interrupt. You set this here. If that event occurs, so you set it here. If that event occurs, it will be in the pending register until your core can service it. Then it will turn into the active state. And we'll talk about how the core knows what to do when you have multiple active interrupts. Yeah.
I'm still a little bit confused about the definitions of interrupt. So using the analogy of calling a contact number, so if there's like 96 interrupt, does it mean that there are 96 like contact people?
Yeah, you could say that. There are 96 plus 16 from ARM possible interrupt service routines that can be written. So possible actions that can be taken. So does that clear it up for you?
Yeah. So what if a person like calling at the cycle, first cycle, and the same person call at the second cycle?
So there's edge conditions where you can have an interrupt service request that's been pulled multiple times and it's being requested faster than the system can respond. In that case, there's no idea, as we'll see later on, there's no way to keep track of how many times that interrupt has been asked. It just says this thing is in pending. So when an interrupt comes in, it goes into pending. It stays in pending. And then you call the interrupt again. Well, it's still pending. It's not pending 3 times. It's just in that pending register. And then it will be serviced in the order defined by that priority table. Yeah.
What's the need to set the bits like on the system do that automatically? Like I get the priorities like important for us to set, but like can it not automatically just pick it up and say this interrupts happens when we set that?
No, well, no. And probably you don't want that. So you don't want, imagine you start up your kit for the first time and every time a GPIO goes off, some random interrupt goes off, right? It doesn't know, you have to program it. And it could be that you're doing a task at the moment, like steering your satellite away from something. You don't want anybody to interrupt you. And so one thing you could do, there's multiple ways of this. One thing you could do is turn off a bunch of interrupts so they don't bother you. So having programmatic control of when you will respond to interrupts is important. Now, your Cube IDE just does magical things for you. You click a few buttons and yeah, a lot of stuff gets enabled. It's good to know underneath that you have control over it.
So let's say it's like you create an interrupt.
Yep.
Before you move that satellite, that interrupt goes into that register and sets everything disabled. And
yeah,
disabled, and then when it's done, it'll set everything back to before.
Yeah, that is a very brute force mechanism that would totally work. We'll find out that you can set your processor to only respond to certain priority levels. And so you basically say, you have to be more important to this to interrupt me. And you can manually set that as well. So there's probably a better mechanism for that, but you can manually enable and disable